Just out of interest, who hasn't heard you speak about this before? There's a few more. Okay, excellent. So, so maybe who's not heard of DSdB out of that group? Just a couple. Okay. So I'm the director of the program that the government funded starting 2018-19 to sort of try to look at this technology called Cherry and what it was and see if it could address certain problems that were evident in the industry. I was actually Director of Technology and Systems in ARM Research at the time. So there's a bit of a swap from being the industrialist to the person working for the government and to work this out. But basically, I came into the government actually as a professor, and I still am at Manchester University in computer architectures. So it was slightly different that I was actually doing a governmental ecosystem, knowing what I was talking about a little bit. But at least it was overlapping at the time. Anyway, so what we have, or had at the time, was the idea that even by 1970s, I actually heard somebody give me an earlier reference than this the other day, that computers and how the way computers work are pretty broken. And there's some, in this paper, there's some lovely quotes. And I think the relative, these are very much true today, if you like. So cannot emphasize the belief that patching of known faults in the design implementation will never give you a secure system. I think we can agree with that today. Keeping up with patching, there's another patch needed. So you're insecure. There's been nothing that changed even since then. And this one, obviously it doesn't quite say secure by design, but secure by retrofit. The idea today that you can patch it and change it to make it secure, when you're starting to talk systems of systems particularly, again, a non-starter. So what's the world like since 1972? Well, we started caring at about 1990s, when people started realising things were really, really broken, and it was a bit late, unfortunately. The DSbD program was about here, so we just had this big jump in the number of reported vulnerabilities, and hey presto, it's still going up at a rate that you really don't want to know about. It's becoming extremely costly. There's a quote, a source there that's reckoning it's around $10 trillion of global GDP lost to cybercrime per year. I'm trying to get, as one of our audience knows, the actual maths that will allow me to say that the UK it's costing us about 30 billion a year in UK GDP in terms of cyber loss. But basically, it's not very good for business productivity and efficiency. So the idea that you could wipe out most of the recent budget simply by fixing your cyber problem is quite an interesting one to think about, yeah? Anyway, so it was a bad world. So by 2018, the stars aligned. We'd had about 8 years of research into Cherry, so they knew that there was possibly a solution to this. We had the industry saying, yeah, I suppose we could do something, could at least look at it. Commercially, they came back and said, no, we're not going to. But luckily, the third metric of that was the government actually asked industry, what are your big problems that haven't been solved? Now, clearly, that was an old, long-standing problem, and the fact that it hadn't been addressed for 50 years made actually the discussion with Treasury quite interesting when they're saying, well, what will happen if we don't invest in this? Will it be fixed? And I says, it hasn't been for 50 years. Why do you think it will now? So we all got together, we got the UK research, and by January 19, we eventually announced government investments into the DSbD program, the Digital Security by Design program. I didn't name that program, by the way, so I forget. Mine was Securing the Future. We narrowly missed it being called the Ada Lovelace project. Okay, so that got voted out just as I started interacting with it. So the vision, as it was at the start of the program back in 2018, is that by next year, we'll overcome the market failure. The market failure that we'd seen that stopped this change for 50 years is that a chip vendor won't build a new chip if there's no software that runs on it. And the software won't write software if there's no hardware. So, and those two markets have the difference between typically a sub-year roadmap and a 10-year roadmap. There's no way they will align unless somebody with a fairly big purse says, let's work together. And that's really what the DSDB program's been all about. It's been trying to get a collaboration between hardware, software, government, business, social economic people all together in a room saying, well, actually, let's address this 50-year-old problem. And the way we'll do it is going in at the foundations of computing. So the ones that don't know Cherry, this is actually, I think, Robert, you've got the next talk and you really say, but it's the low-level way that a computer runs software that's changing. Okay, so people, I've spoken to some quite technical people in my academic role. Oh, you mean you're adding a new BIOS layer? Nope. We're changing the way a computer runs software. Oh, you're doing trust zone? Nope. We're literally right the way down as the model of computing, which probably started, late 40s, guys? 40s, 50s? Where the idea that a system has an indexed array of memory that you read values from, do something on it and put it back. That's still how most computers today work. We had a small detour in the 70s when they said, well, actually a stack's quite a nice way of doing it, where you don't have a global memory. But in essence, we had to go back and look at, for the first time at scale, can we change that way that a computer actually runs memory? And obviously the alignment of the vision here and the vision of NCSC are all pretty much the same. It's a societal global problem as opposed to a specific business sector that needs to improve. So the programme, basically I like to view it as a facilitator. Obviously it needed its objectives, it needed to bring the groups together. That's probably one of the biggest things I think that the programme has done is that we've been running all hands meetings where we pull a couple hundred of the ecosystem together on a twice-a-year basis, and the different faces that you see in the room in terms of where they come from, what their responsibility is. Typically when we see an ecosystem, it's like companies with like minds trying to do the same thing. Okay, so think about the number of ecosystems that you're in, but this is not sectoral based. It's the fundamentals of how a computer works. It's an economic thing. It's how do we actually convince, people what policies are required. We've had people looking at the PSTI bill as an example of how you can bring that in slowly. What are the effective standards? Do we have a checkbox? Does the hardware need a standard? Probably not, but of course the implementers need to know what they're implementing, but the deployers, you don't want it to be a tick box, as Paul was saying. It needs to be a mindset change. And one of the mindset changes we've been working on is actually think of net zero. At what point did the consensus become that the environment and the sustainability became a problem of a concern of everybody? Okay, at that point, hopefully the vendors will actually see a reason that they need to differentiate and do this. Because if everybody has that move over to, well, actually, is it really acceptable that I'm shipping a product that's got a 50-year-old known class of vulnerability in it, that, no, it's okay, I don't get liable, I don't get sued for it, it's the user of my system that's responsible and pays the bill. That's got to change, and that's obviously where some of the engagement's been going on, and obviously we have been funding as well. The programme itself actually ends as the DSDB programme against its original objectives in March. So in that regard, it's great to see the group here today, where I can say I had nothing to do with bringing you all together, where the industry people are actually starting to come together with the academics now to basically follow on and continue what needs to be done in terms of deployment and adoption and diffusion of the technology. It's not to say that the government may or may not help with that, but the original DSDB programme as defined will come to an end in March. So why was it that we thought that a few academics over in Cambridge University chatting to a similar number of people in ARM could actually change the entire world and the way that softwares have run for 60 years? Okay, now what it was two things. One, first, the stack, and I'm sure a lot of you have heard me talk about the stack, where today, basically, it's the billions of users being told, don't click on that. Yeah, because the likelihood that's another vector into a vulnerability in your machine that will open something up. Yes, there's pure user where they'll go and give away the secrets and things, but in essence, a lot of them view this page and I've got a vulnerability in the browser that opens up your machine that allows me to go and read your credentials, that takes over your network, and bang, you've lost everything. Yes, it's a user click, but in essence, it's the technology stack under them, not protecting them. So what we've got to start doing is moving down that supply chain technology stack. The language that's coming through, or what language that I've been promoting now since pre-American government picked it up as well, which was good, is manufacturers must deliver more secure applications and services. That's an attack surface reduction. Okay, lots of ways you can do that. It's not going to block a vulnerability, but hopefully there's less of them. And you've got to ship that with a configuration by default that means you're not just basically giving somebody with a huge stack of interfaces and click buttons and everything else that will cause that problem. So by default, let's bring down that attack surface. Lots of practices to do that. But still, the components and the systems within that need to look more against how they can protect the user. Any academics here and will know if I say leaky abstraction, that's often where a lot of these errors comes in. It's the interfaces between the modules. The fact that you can build and link a JPEG library into your key management system, you get the idea, but then you might not do that. That if there's a vulnerability in the Huffman decoder, how many people have come across that one last year? It opens up your machine and takes over, in this case, your phone and your browser and your laptop and your server, just by viewing an image. That abstraction in the way that libraries work, it leaks, it opens up the whole of your machine. The Cherry technology, in my view, is the abstraction between the hardware view of memory and the operation and software's view. So that's the abstraction. That's also the one that's been giving you an awful lot of the Spectra, Meltdown, that kind of issues as well. And it's by design. Now, it's not just a hardware thing by design. It's thinking about how can I protect the user of my component from the system that they are building. Okay, what is it in the design of the thing I'm building that actively protects in my creation of it from the possible vulnerabilities or leakages of the abstractions, etc. And that for me is what the by design is. We are seeing people pushing this all the way up into the lifetime management of a system, and I'm going, well, how's that protecting me in the first place? I would like to try to pull that back down into, it's the components or the subsystems that build the systems. Now, clearly, a mobile phone could be a component of a bigger system. So it could be that I have to, you see what I mean? It's a very, very nested and hierarchical. Now, the hierarchy of the stack that we work with in the Cherry area comes all the way down. Obviously, you've got the hardware platforms, your CPUs. I reckon there's around 3 architectures of importance. And I say there's approximately one way that that computer will then access and interact with memory. Okay. There's a few weird ones, but there's basically that one way, and that's where the change is. So if you can get the, tens of people in the world that define that for their architectures to agree, and that's one of the things I'm hoping, or we are seeing this Cherry group do, is define that standard change required for an architecture, okay, or architectures. Change that, you change it for the billions and every customer above you. Okay, so that's what is all about. Going back to the program itself, we, 2018, I think it was, sit down, well, how are you going to change the world? And this was the way we did it. We sort of said, we've got to go and get that enabling technology done. At the time, the budget wasn't as big as I asked, and I had to make the interesting call, RISC-V ARM of it. Well, ARM, okay, we'll focus on ARM now. Obviously, you will see that there's been a lot of work in the last 2 years to also bring RISC-V into it as well, because we, luckily, thanks to departments, managed to grow our budget back up from what we started with. But basically, the idea that we could prototype the hardware-software environment for the technology sector, the people that actually build either the tools or the libraries or the code, there's been a huge amount of work in proving that software does work. I think there's no class of software that we think couldn't work on a Cherry system today. So some of the really advanced things that people do in dynamic code generation and things like that, yeah, it still works. Okay, so we're seeing that happening. And then if you can remember the line I didn't speak about on the vision, we'll also allow a few industries to have a look. Okay, clearly for an industry, it means that there's no product, because it was a research program in that regard, proving the thing out. But it was important for them to start understanding, is there economic benefit to being able to see that a bug was predictable in the development flow. And we've actually found quite a lot of those across the partnerships where they said, yeah, well, actually, we were having a problem with our, let's take an example, scanner that we had in our network e-infrastructure that kept failing about every month. And it was really bad because it was really, impactful to the system when we had to restart everything. We decided to port it over, try it, and within an hour or so they went bang and debugged it. It became a predictable bug that could have been caught there as part of their development. That actually kicked another thing off in the program, which is something that we're calling the Cherry Remote Lab, which allows basically a software developer to try their software on this architecture as part of their test and validation process that will highlight the bugs pre-ship and then ship on traditional hardware. So in essence, it's a way of bringing down that attack surface. So Remote Lab, you should hear more about that in the near future, but I think it's alive at least for evaluation purposes today. It runs in the cloud, fits into GitHub, target, send the code off to that system, fuzz it, come back, get all your reports of where it may or may not have failed due to vulnerability systems. So again, you don't have to deploy on Cherry at that point. Clearly, it's a static test in that regard, but at least it'll help you get the bugs out before you actually ship the product. So going back to that ecosystem, this isn't all of them because we have the Technology Access Program from Catapult and some other sub-projects as part of the hub. But basically, what we did is we pulled together this cross-cutting ecosystem of academic focus, this group of competitions. How do you use it in verification? So the idea of the verifiers today is that they don't actually know how a computer actually works, they're just guessing. Okay, so one of the big problems of formal verifiers today is their memory model is very weak. They say, you've put a value into a variable, you assume that it's going to be the same when you read it. No, that's not how hardware works, guys. So, there are those kind of vulnerabilities, and we have had high integrity people actually fall foul of that, where they've used all of the high integrity tools to find an error, run it on this, and it goes bang, and they go, oh dear. Okay, so that's quite interesting. We also ask them what does it mean to current software and libraries? Can you really run an entire stack? Well, I think you've got the demo, isn't it here? Yeah, I won't spoil the example of that basically says yes. And then the future implications. I think this was one that I wasn't expecting at the beginning of the program, but a few researchers are saying, well, actually, we can change the way we do things today. Okay, some of the things that people do today, virtual machines, compartmentalized Dockers, that kind of thing, are very heavyweight in terms of what they can do. There was one academic put basically some Lambda function services in there, and they were jumping up and down 300 times faster than they do on their desktop. Okay, we weren't expecting that kind of change. That's just the idea, but it still has, if not better, hardware isolation around what those systems were using. Again, technology driven, and then the social economic, actually asking some of the political questions, the economic questions as well. It's found its way into various papers, strategies, a couple from the UK here, the two that Paul mentioned that have gone over to the US. I think it's 17 countries at the moment, isn't it, signed up for that, and then obviously the White House, see what happens with that. But also in terms of anchors in the UK strategy, there's two main documents there, as well as the sort of not quite so explicit, but the integrated review, the idea that hardware does matter for national security. So where are we at, really, at the end? What I'd like to propose is actually we've shown that hardware and software can reach this point of where around 70%, and that's not just a desktop number, we're seeing that in embedded as well. We've got evidence in that in the automotive market as well, for example, and basically get the tools in the environment up to a level where actually it is ready for commercial adoption, which is why we're seeing commercial people here already with roadmaps and products announced to bring that. It's the language, the idea that we can do more, getting that communication out into the system. We're seeing this international ecosystem, this one, growing up around alignment of the standards and the enablement. And the pledge, the one that I don't think you did mention, that's the enterprise companies, basically 200 plus of them saying, yes, we'll do something in this area as well. Okay, so those are international companies signing up to a pledge. It'd be great to see some more people pledging and saying we're doing it with Cherry, or we're doing it with memory safe technologies to protect the systems, like I say, businesses, but there's still work to be done. I think that's the last thing. Obviously, Paul mentioned I loved your chart actually, at this push-pull. Increased awareness and collaborations, helping the supply chain actually make those decisions that head us in the right direction, but also making sure those end customers know that more can be done. And I think that will be the biggest change, is where the customers will start saying, and where's your memory safe roadmap? Are you shipping me code that isn't isolated? What's the criticalities of all the different levels of code you've got in there? How are you protecting one supply chain to keep everything isolated in a way that doesn't make the system grind? So with that, and minus 5 seconds, yeah, thank you very much. That was all I had to say. Thank you.